Next, we're going to talk about half-lives. Every radioactive isotope has a characteristic rate of decay. So we determine this rate by measuring the half-life. So the half-life is the time required for 1/2 of the radioactive isotope's nuclei to decay. So once a half-life occurs, you're going to have half of the original amount that is still radioactive. The other half will have decayed into another isotope. So here we have a good example of a visual of this. So with potassium, we have a radioactive isotope when a new rock is formed. What ends up happening is this specific isotope of potassium has a half-life of 1.3 billion years. So with that 1.3 billion years, half of the radioactive isotopes have decayed. In this case, they're decaying either into calcium or argon. So this one is unique in that it has two different decays that's occurring. We still refer to it as one radioactive decay in that 1.3 billion years. So 1/2 is still radioactive, 1/2 is no longer radioactive. After two half-lives, now we have half of the half, which is a quarter, remain radioactive. And then the other 3/4 are stable. And so on and so forth. Now, the interesting thing that happens with this is that so there's probably about 40 dots in this example. In real life, a sample of a specific radioactive isotope has trillions and trillions and trillions of atoms in there. So it takes a really long time for it to occur, and the other thing is that this never really gets to zero. We're always taking half. So eventually, in this example, after 4 half-lives, we have 2 radioactive atoms left, but in real life we would have an innumerable number still. So we would approach zero, but we would actually never get to that point. So there's 2 equations that we need. Sometimes we'll end up using one or both. So the first one, we have the original mass times 1/2 to the nth power is equal to the final mass. And then the second one is how we calculate n. N is the number of half-lives again. It's the same n. T is the time elapsed. I like to think of this as total time. So it's the total time that radioactive decay is occurring, while T1/2 is the length of a half-life. So taking a look at our example here, we have fluorine 21. It has a half-life of 5 seconds. So we looked at potassium. It has a half-life of 1.3 billion years. Fluorine, on the other hand, has a half-life of 5 seconds. So there's half-lives everywhere in between, some even longer than the potassium, and then some even shorter than fluorine 21 here. So we have 5 seconds. This is our T1/2, which is referred to as our half-life. We have to start with 25 grams, so this is our original mass, or our MO. How many grams would remain after 60 seconds? This is our total time, so it's just our T. So in this problem, we will actually need both equations. MO times 1/2 to the nth power is equal to MF, and then N is equal to total time over half-life time. So let's start with calculating N. We have 60 seconds divided by 5 seconds, which gives us a total of 12 half-lives. Notice this 12 doesn't really have any units, it's just 12. So that ends up being our N value. So we can then calculate this in our next equation. We'll have 25 grams times 1/2 to the 12th power is equal to MF. So you want to be careful when you plug this into your calculator. You have to put the 1/2 in parentheses with the exponent of 12. You have to do that part first if you're splitting it up. You should end up with 0.0061035.156 grams of our radioactive isotope remaining. Now, in terms of sig figs, the sig figs for these types of problems, what I would like for you to do is just look at your original mass. So your original mass has 2 sig figs, so your answer should have 2 sig figs. So it would be 0.0061 grams of your radioactive isotope. The remaining 24 grams are still there. They have decayed into the next isotope. So in this example, we have plutonium-239. Its half-life, or T1 half, is 24,100 years. We have an original mass of 100 grams. How much remains after 96,440 years? So that ends up being our T, or our total time. We're also given our original mass. So this problem is very similar. Usually you'll end up solving for your final mass in these types of problems. So what we're going to end up doing, we're going to first use our N equation to solve for how many half-lives are occurring. So our T is 96,440, that's our total time, and 24,100 years. Notice how my units are matching. You could potentially have a problem where you have hours and minutes, or years and days, or something like that. You just need to make sure your units are matching for this, or else your answer won't work out correctly. So we're going to end up with 4.0016. Usually this is a whole number, so we're just going to leave it at 4. For our N value, 4 half-lives have occurred. We're then going to take our 100 grams, which has 3 sig figs because of the decimal place, times 1/2 to the 4th power, which is equal to our final mass. So 100, plugging this into our calculator, gives us a final mass of 6.25 grams of our radioactive isotope remains for this one, for plutonium-239. So again, this one has a really, really long half-life. It's kind of somewhere in the middle in terms of length of half-lives. It can be kind of all over the place. So this would end up being our final answer. I have 3 significant figures because I started with 3 significant figures for my initial mass. You could have a problem that you would solve for MO. You would follow the same process. The only difference is you would just have to rearrange your equation slightly. So you would take the 1/2 to the nth. You would take that as a whole and divide both sides by it if you were solving for the original mass. But that's half-lives.